First, we need to describe the two-photon states that come out from the lab process where we're talking about down conversion. So we have the signal photon, that's one of the generated photons. The other is the idler photon. And we, of course, put in the pump photon to drive the whole process. So we've talked about it in the lab, but we should remember that energy is conserved. So we can say the frequency of the pump photon is equal to the frequency of the signal photon plus the frequency of the idler photon. And so that's just a statement of energy conservation, which means that when we put in an ultraviolet photon, we get out two infrared photons with longer wavelengths. What we need to do now is specify the state of these two photons. So we've talked about single photon states before, but now we're going to look at two photon states. In particular, we could say that the idler, or the signal photon, let's say, is in the horizontal state, and the idler photon is in the horizontal state. So we label these with a subscript. That's a reasonable way to do that. S for signal, and I for idler. So formally and technically, we need to write this state as a single state. And the way that we can do that is to specify the signal and the idler photon within the ket. Technically, this is represented by the direct product of the two vectors. The direct product is indicated by this circled X, and we'll talk about what that means in general in the next page. We'll look at an example. So that's the direct product. As an example, we can look at the direct product between two vectors, and we'll look at two-dimensional vectors first, since that's what we're most familiar with. Take the vector 1, 2, is the direct product of the vector 3 and 4. We get the result 3, 4, 6, 8, where we notice that's now a four-dimensional vector, and it comes from the fact that 1 times 3 is 3, 1 times 4 is 4, 2 times 3 is 6, and 2 times 4 is 8. So you'll notice that the 1s come from the first element of the initial vector, and the 2s, we'll circle in orange, come from the second element of that first vector. So you're sort of distributing that first vector around through the second vector in a multiplicative way. So if you look at the dimensions, you'll see that the first vector has two dimensions, right? It's two element. And the second vector also has two dimensions. And the product resultant vector has four dimensions. So the vectors that come out of direct product multiplication live in a larger vector space. So we'll start to build some of these up. But these two-dimensional, these two-particle states need the extra dimensions because there's essentially, when you've got two states for each of the two particles, then there's going to be four combinations, right? And you can see how that would work or generalize to larger dimensions. So you'll build some of these up with the notebook that you'll do shortly. The first four that we want to look at are the combinations of how to put together the H and V states, right? So we have H and H, so the signal and idler are both H. And you'll find out that's the 1, 0, 0, 0 state. HV is the 0, 1, 0, 0 state. AVH is the 0, 0, 1, 0. And VV is the 0, 0, 0, 1 state. So those are the four possible ways to combine H and V states. Now operators we can form the same way. We want to combine them using the direct product, and we just need to keep the same order. right? So if we had the signal photon first and then the idler photon, then we put in the operator for the signal photon and take the direct product with the operator for the idler photon. So if, for example, if we want to project the idler photon into the H state, then we have, and leave the signal photon alone, like we don't want to do anything to that photon, then we simply take the direct product of the identity operator, because we're leaving the signal photon alone, direct product from the identity with the projection operator, the pH operator. Right? So whichever the operator is first is going to operate on the signal photon, whichever operator is second is going to operate on the idler. So we could do the opposite, right? We could project the signal into the H state and leave the idler alone, and that would be the direct product of pH, the projection operator, direct product with the identity operator, which leaves that second photon alone. Right? So again, identity operator is the trick for leaving a photon unchanged. Alright, so we always treat the photon state by using the signal first, then the idler. So if we did want to make a measurement operator that measured one of these photons, we could measure, say, the signal photon and leave the idler photon alone, and we'd put in the measurement operator that we're used to, take the direct product with the identity operator. And similarly, if we wanted to measure the idler photon, we could put in the identity in the first position, so the identity acts on the signal, and the measurement operator in the second position, so the measurement operator acts on the idler.